All right, Chapter 4 review, page 421. So these are the problems to take notes on, to copy and do. Number one, first one. Directions say, draw the graph of the inverse of the given function. So you remember the inverse of a function, the x and y values are switched, are reversed. So if we are going to draw the graph of number one, we just need to look at each of the x and y values and switch them. So if I start on the bottom left where it had negative 6, 0, I now have 0, negative 6. And instead of negative 3, 1, we have 1, negative 3. And we'll just continue doing this all the way up through each of those values. Obviously the 0.33 does not change. And there's our graph of the inverse. You may remember that that graph is going to be a reflection across the line y equals x of the original graph. Moving on to number 3. The directions say use composition of functions to determine whether the given functions are inverses of each other. F of x equals 2x minus 5. And g of x, x plus 5 over 2. So in doing compositions, we need to do f of g of x. And this solution should equal x when we are done. Then we're going to reverse it, do g of f of x, and that solution needs to equal x when we are done. And if both of them equal x and we're completed and simplified, then that is a proof that these are really inverse functions of each other. So f of g of x says take the g function and place it into the f function. So it'll be 2 times my g function, x plus 5 over 2, and then we'll continue the f function minus 5. So if I multiply by my 2, they would cancel. I get x plus 5 minus 5, which simplifies to x. So far, so good. G of f of x is taking the f function and placing it into the g function. So we'll be placing the f function right there. So in that x location, it will become 2x minus 5. Then we'll continue the g function with plus 5, all divided by 2. So simplifying this, well, the minus 5 plus 5 are going to cancel, and I get 2x over 2, which reduces to x, and check. That is a proof that those are inverse functions of each other. Number 9, and the ones I'm choosing, remember, are just every other one on your syllabus for the review of Chapter 4. So I'm just picking every other one. Number 9, directions. Find the inverse of the function, sketch the graph of the function and its inverse on the same set of coordinate axes. So our first one, h of x equals negative a half x minus 2. I'm going to go ahead and sketch this original function. So this is just a line. It's in slope-intercept form. Negative 2 is my y-intercept. Negative 1/2 is the slope, so down 1 over 2. So here is our original function. I'm going to label it as h of x. It's the original one. I'm going to work on finding the inverse of this function. So the steps to find the inverse, I first write it in y equals form. And then we switch the x and y, so it becomes x equals negative 1/2 y minus 2. And then we will solve for the y. So adding 2, x plus 2 equals negative 1/2 y. And then multiplying everything by the reciprocal. So if I multiplied by negative 2 on both sides, that would eliminate that negative 1/2. I'd get negative 2x minus 4 equals my y, or I could say y equals. Then I'm going to write it in the inverse function notation. Since this was h, I'm going to say h of x inverse equals negative 2x minus 4. So there's the answer to what is the inverse function. Then graphing it, negative 4 is the y-intercept of this one. Negative 2 is the slope, so down 2 over 1. I will then label this one as my inverse function. Negative 1 up there. I'm going to draw, they didn't ask us to do this, but I'm going to draw that line y equals x. And notice these are reflections of each other. That blue graph and the green graph, if I rotated them or reflected them across that dashed line, y equals x, they would form the other image. Number 16, it's the next one. Directions, solve each equation. Don't use a calculator, so we should be able to simplify this. Natural log of e to the pi equals x. You want to have memorized the properties of logarithms. So there's a little table that talks about properties of logarithms where we know the solution just automatically. And you'll have to leaf back through the book. I'll see if I can quickly find it. Yeah, basic logarithm properties are on page 360. And this one happens to match number 3 of those rules. Natural log means it's log base e. So if the base of the logarithm and the base of the argument, the thing I'm taking the logarithm of, match, then I know what my answer is. They said equals x. My answer is just this exponent pi. X equals pi. We're done. So we need to know those basic properties, and that allows us to quickly solve a problem like 16. 18. 5 to the x minus 4 equals 625. I'm going to be using those properties again, and one of the properties talks about if my bases can be written the same. This 625 is a power of 5. I copy it. 5 to the x minus 4 equals 5 to the, let me double check here, make sure I'm raising it to the right power. The 4th. So if 5 to the x minus 4 equals 5 to the 4th, that implies that x minus 4 must equal 4. For these two things to be equal to each other. Solving this, adding 4, x must be 8. We are done. We have our solution. 26 is the next one. They want us to sketch the graph of these functions. So 26 is f of x equals 1/4 to the x. So these are exponential equations, exponential graphs. And there are two basic kinds of exponential graphs. We have the increasing function, And that's where our base is greater than 1. And then the decreasing function. And that's what we have here, where our base is between 0 and 1. Now, all exponential graphs, if they have not been moved, translated around, go through the point 0, 1, and 1, the base. So this one has not been moved at all. It should go through 0, 1, 0, 1, and 1, the base, 1, 1/4. In this case, because our base is 1/4, 1, 1/4. Now I know it has a horizontal asymptote right on the x-axis, so I know this thing comes down and doesn't ever hit the x-axis. And back to the left, I just need a couple of points so I can see how steep that curve is. So I'll make just a little table of values. I'm going to choose a -1 and a -2 into my equation. So if I take 1/4 and raise it to the negative first, well, a negative exponent is just going to flip that fraction. It becomes 4 over 1, or 4 to the positive first. And if I have 1/4 raised to the negative second, it flips the fraction 4 to the positive second, 16. Back 1 at 4. If I go back 2, I'm at 16. It's already way off my graph. This is really steep as it heads up. So there's a good accurate sketch of that exponential decay or exponentially decreasing function. Number 30, f of x equals 2 raised to the x minus 3. Now this one is an exponentially increasing function, or growth function, because that base is greater than 1, that base is 2, I know it's going to be increasing. So again, if it hasn't moved, and this one has moved, talk about that here, if it hasn't moved, it's gone through 0, 1, 1, the base, which is 2, but this one is going to have moved. That minus 3 on the x says it has moved to the right 3. So if I figure out my new point, instead of 0, 1, if I've moved to the right 3, it's now 3, 1. And instead of 1, 2, moving to the right 3, it becomes 4, 2. So those should be 2 points on this graph. 3, 1, 4, 2. I know this tail down here doesn't ever hit the x-axis. I'm going to be curving down something like this. And I'm going to get another point or 2 off to the right. Table of values. See if I can fill that in accurately. I'm going to use a 5 and a 6. And it may end up that it goes off our graph. So 2 raised to the 5 minus 3. Well, that's 2 squared, which is 4. 2 raised to the 6 minus 3, that would be 2 cubed, and that's 8. So it looks like this one fits pretty well. 5, 4, 6, 8. I can continue my curve going through those points. And there's our graph of that exponentially increasing or exponential growth function. 32, logarithm graph. F of x equals log base 1/3 of x. Okay, logarithm graphs, since they are inverses of exponential graphs, have the x and y switched from what the basic exponential does. So logarithm graphs that have not moved go through 1, 0 instead of 0, 1, and base, 1 instead of 1, base. So for this one, 1, 0, there's a point on my graph. Base, my base is 1/3. 1/3, comma 1. Over 1/3 up 1. And logarithms, instead of having the x-axis as a horizontal asymptote, the x and y is switched. The y-axis is a vertical asymptote. So this one has something coming up that doesn't ever really hit that y-axis. And then it goes off to the right. This is a decreasing logarithm function. So I'm going to pick a couple of values off there to the right. Let's see. Let's use a 5 and a 10. So if I do log base 1/3 of 5, now we're going to use a calculator in that change of base formula that we learned. So if I take the log of 5, I'm going to choose natural log, though it doesn't matter if you do natural log or common log. I'm going to do log of 5, natural log of 5 divided by natural log of 1/3. So you can try that while I am trying that. Make sure you are using parentheses around your 5 and your 1/3, or 1 divided by 3. Should get negative 1.5 approximately. Log base 1/3 of 10. I'm going to do the natural log of 10 divided by the natural log of 1/3. Negative 2.1 approximately. Over 5 down 1.5. Over 10 down 2.1. So it doesn't drop down very fast at all. And there's our logarithm graph. It's a decreasing logarithm function. It's decreasing because that base is between 0 and 1. If it was an increasing function, that base would be bigger than 1. If I had log base 2 of x, then my graph roughly, it would still go through the point 1 comma 0, but it would be coming up something like this. That would be an increasing logarithm because the base is bigger than 1. 43, next one. Change each exponential equation to its logarithmic form. So 5 cubed equals 125. That is in an exponential form, 5 raised to an exponent. So if I change it to its logarithm, log base 5, the base of the exponent is the base of the logarithm, of 125 will equal the exponent 3. So memorize the locations of where I put the base. The base on the exponent is the base on the logarithm. And the answer to the logarithm is the exponent. Logarithms find exponents for us. So just memorize the locations that we switch those numbers to, and it becomes easy to switch back and forth. From exponential to logarithm, logarithm to exponential. 52. Write each logarithm expression as a single logarithm with coefficient of 1. So 52 is addressing the properties of logarithms that allow us to either condense or expand. 5 times the common log of x minus 2 times the common log of x plus 5. A couple of things I noticed to start with. This 5 in front is going to become an exponent. That 2 in front is going to become an exponent. And the subtraction comes from a division. So when I condense it down to one logarithm, I know I'm going to have a division problem because that minus. And instead of x, I'm going to have x to the 5th. And that was first, so it's in the numerator. And instead of x plus 5, I'm going to have x plus 5 squared. So we have condensed it down to one logarithm. Nothing we can simplify in that fraction. So that is going to be our solution to number, what was that, 52. Our solution to number 52. 58. Use the change of base formula in a calculator to approximate each logarithm accurate to 6 significant digits. 58. Log base 8 of 0.3. All right, change of base formula, did it a minute ago. I can take the log of 0.3, and again, I'm going to choose natural log, just kind of a personal preference, divided by the common log, the natural log of 8. You could use common logs as long as you did it both with common logs. 0.3, better make sure I have a decimal there. So let's try that. They said the 6 significant digits, 0.57, 8, 9, 8, 9, 1, 2, 3, 4, 5, 6. If I round it off there, 6 significant digits. There would be our solution. Number 60. Solve each equation for x, give exact answers, so that you don't need to use a calculator on these. So number 60, 5 to the x plus 1 equals 41. Okay, so if I'm trying to solve for that x, it's in the exponent, so I'm going to need to use logarithms. So I'm going to rearrange this into a logarithm form. My base is 5, so I get log base 5 of 41 would equal my exponent, which is x plus 1. I'm trying to solve for my x, so I'm going to subtract 1. I'm going to write my x first. I have log base 5 of 41, and I'd have to subtract 1. Now there's one more step. A change of base formula here. Log of 41, I decided to use common log this time, over log of 5 minus 1. That's my answer. That's as far as I can go without a calculator. They didn't want us to use a calculator and go to a decimal. They wanted us to simplify that without a calculator. 62 is the next one. Directions, say solve each equation. I guess it's the same one. For x, give exact answers, do not use a calculator. So natural log of 3x plus natural log of 2 equals 1. Okay, well I am adding two logarithms so I can condense them together by a multiplication problem. Natural log of 3x times 2 equals 1. Oh, that would be natural log of 6x equals 1. I'm trying to get to that x. Since it's in logarithm form, I'm going to change it to exponential. And the base of a natural log is e. So my exponential base e raised to the first equals 6 times x. So if I want to get x by itself, I just need to divide by 6. And e to the first can be just written as e over 6. There we go. That's the exact answer for what x is. Calculator could get us to a decimal, which we do not want. We want the exact value just by hand rearranging it. 75. Earthquake magnitude. Determine to the nearest tenth the Richter scale magnitude of an earthquake with an intensity of I equals 51,782,000. So we need to know our magnitude of an earthquake formula equals the common log of intensity divided by the zero intensity earthquake. So if this is our intensity value, then I can replace my I with that value. Common log of my I is 51,782,000 I sub 0 divided by I sub 0. Well, our I sub zeros would cancel, and it just becomes the common log of 51,782,000, which we will now try. Oops, wrong number. .7. Magnitude of the earthquake, 7.7. 79. Chemistry. Find the pH of tomatoes that have a hydronium ion concentration of 6.28 times 10 to the negative fifth. They want us to round to the nearest tenth. Okay, so pH is what we're trying to find. Well, I need to know that the pH is the negative common log of the hydronium ion concentration. So there's our formula for how we get pH. So they tell us that the concentration is 6.28 times 10 to the negative fifth. Becomes a calculator problem. Make sure you can enter that scientific notation number in your calculator. And you get 4.2 rounded to the nearest tenth. Power of the hydrogen. Remember, if something is acidic, it is below 7, so that's kind of acidic. Basic, above 7. 7 is neutral. 81. Compound interest. So there's some formulas that we need to make sure that we understand. The amount after we invest a principal, 1 plus r over n raised to the nt. Make sure that one is memorized. They say on number 81, find the balance when 16,000 is invested at an annual rate of 8% for 3 years. At part A, it's compounded monthly. So part A is going to use this formula, periodically compounded interest. Principal, 16,000. Times 1 plus, our rate is 3%, 8%, so that's 0.08. Number of times a year it's compounded, they say monthly, that would be 12 times. Raised to the 12 times 3, because we're doing it for 3 years, that also is the number 36. Might be easier to enter it that way in your calculator. So try it out on your calculator, see if you can get the right answer. I'll try it out. $20,323 and 79 cents, rounded to hundredth because that is where our money is rounded. This should be accurate to the penny. Part B, they want to know continuously. So here's our second formula you need to make sure you've memorized. A equals P e to the RT. Hurt. Continuously compounded. Same numbers. So our amount should equal our principal of 16,000. E is raised to our rate, which is 0.08, and our time is 3 years. So just substituting it in, or putting it in the calculator. $20,339.99 when you round that. Again, should be accurate to the penny. Make sure that you are trying it on your calculator. You want to know now if you are entering it correctly, know how to enter it correctly, so that if you're not, you can get help and get that corrected before I may test you on it. 84. Medicine. The skin wound heals according to the function given of n of t equals n sub 0, so that's an original thing, e to the negative 0.12t. And they'll explain to us what every variable is. Capital N is the number of square centimeters of unhealed skin, t days after the injury. N sub 0 is the number of square centimeters covered by the original wound. So this formula gives us how much is not healed, number of square centimeters of unhealed. Part A, what percent of the wound will be healed after 10 days? Well, let's use this formula. It will tell us how much is not healed, and then whatever that percent is, we can take it from 100% and know what is not healed. Or what is healed, because that's what they ask. How much will be healed after 10 days? Okay, n sub 0, what percent? Did they give us? No, they just said what percent. So originally, I'm going to call my original amount 1 for 100%. E to the negative 0.12 times 10 days. And let's get our answer for that. And remember, this stands for unhealed. $30.12. If I write it as a percent, 0.3012, that's 30.12%. Well, that's unhealed. But their question was, how much is healed? So if we take 100 and we subtract our answer from that, 69.88. 69.88 must be healed because 30.12 was unhealed. Part B, how many days to the nearest day will it take for 50% of the wound to be healed? Okay, well, 50% healed also equals 50% unhealed. So if I'm saying I'm starting with 100%, then I want to end up with 0.5 at the end. E to the negative 0.12t. And we're going to try to solve for the t, how many days it takes for us to arrive here. Well, isolating that exponential e, divide by 1, so that doesn't change. 0.5 e to the negative 0.12t. I want to change it to its logarithm form so I can get to this variable in the exponent. If it's base e, that means natural log. Log base e of my 0.5 must equal my exponent, which is negative 0.12t. So as long as I divide by negative 0.12 to isolate that t, it should tell me the number of days. So natural log, and again, try it on your calculator. Make sure you can do these things. And, oh, I entered it wrong. Make sure I can do these things. 5.8. Approximately 5.86 days for half of that wound to heal. Part C. How long to the nearest day will it take for 90% of the wound to heal? All right, so if 90% is healed, it means 10% is unhealed, and that's what our formula gives us. So we want our answer to equal 0.1. We start with 100%, we only end up with 10% unhealed. E to the negative 0.12t. This is really very similar to part B. We're just needing to be able to analyze the question and use our formula properly. So dividing by 1 doesn't change it. E to the negative 0.12t. Change it to logarithm form. Natural log of 0.1 will equal my exponent. And then isolating that t, dividing by a negative 0.12. Let's see what we get. 19.2, so it's going to take us about 19 days. And then 90% of that should be healed up. Number 90. Carbon dating. Determine to the nearest 10 years the age of a bone if it now contains 96% of the original amount of carbon-14. It says the half-life of carbon-14 is 5,730 years. So this is a basic exponential function that is going on. So we have just a general exponential equation that we can use to help us solve this. If you look back at page 391 and 393, there are a couple of approaches we can take. I want to first take that general exponential equation. The number, the amount of something I have at time t will always equal the original about e to the kt. That's back on 391. I think is where that is. Yeah, it's on 391. So if we use this approach, we're going to need to take a couple of steps on this. It says that it has a half-life of 5,730 years. So we need to first figure out what the constant is that goes with this carbon-14. So if I have a half-life, I'm starting with 100% and I end up with 50%. E to the k times 5,730, because that's the time it takes for this to happen. We want to solve this for the k. Now dividing by 1, 0.5 equals e to the, I'm going to change it to logarithm form, so base e, log base e, of 0.5 will equal that exponent. Then we can divide by our 5,730, and that will give us the constant value that works here with carbon-14. So let's do that here. Negative 1.2, negative 1.20968 times 10 to the negative fourth. So if I wrote it not in scientific notation, I have to move that decimal 4 places. Oops, forgot to put my decimal. That's moving in 1, 2, 3, 4 places. And I need to have this constant out to a long ways, because these are very sensitive to rounding, and I don't want to round that too much. Now that I have the constant, I should be able to answer their question, which was, let's see, what are we on, number 90? Determine to the nearest 10 years, so round to the nearest 10, the age of a bone if it now contains 96% of the original. So if we contain 96% of the original, we're equaling 0.96. We started with 1. E to the k, which I now know, negative 0.000120968 times t. And we're just trying to solve for the t, which is up in the exponent, so it's the same process. Now dividing by 1, it's gone. Change it to a logarithm. Natural log of 0.96 equals our exponent. And then we can divide by this lovely number on both sides. We'll divide it over here as well. We'll round this answer to the nearest 10 years, so try that one. And it says 337. So 337 rounds to 340 years for the nearest 10, the nearest power, the nearest tens place. Let's see, number 93. Last one, 93. We learned about logistics growth problems. It says the population of coyotes in a national park satisfies the logistic model. P sub 0 is 210. That's the original population, and it was in the year 2001. C is 1400, so that's our limit to growth. And they tell us P of 3, so 3 years later, which would be 2004, the population had reached 360. So getting all our information down, our original population was 210. And that happened to be the year 2001. And our limit to growth is 1400, our C value. And they tell us the population 3 years later was 360. So we need to know our logistics growth formula. Population at time t. Logistic growth formulas, C divided by 1 plus A E raised to the negative BT. And that B could be a K, it's just a constant up there. And the second thing we need to know is how to get our A value. And our A value we learned is C minus the original population divided by the original population. If you look in your book, back on page 421, they write the logistics model. It was in section 6. You can go back to section 6 and you can find those two things. But on 421 in the review, they write that out. So let's start by finding our A value, because we know everything we need to find our A value. So our C is 1400. Original population is 210. Divided by 210, our original population. If I simplify that, I'm not going to go to a decimal. 17/3, because I want to try to keep this accurate. If I go to a decimal, that's going to cause some rounding error into this thing. So the first thing, I got my A value. Now the next thing I'm going to do is I'm going to fill in this population with the information I know. I know a population 3 years later is 360. So I know what this value is. 360 must equal, well, my C is 1400 divided by 1 plus A is 17/3, E to the negative B times 3, because I know my time is 3. I could have written it as negative 3B, but I'll just put it in that order for just a moment. So there's only one unknown, that B value, that we need to get to. So I'm going to get rid of this fraction. I'm going to multiply by that denominator over here on the 360. So I get 360 times 1 plus 17/3 e to the negative, I'm going to write it as 3b this time, and that must equal 1400. So I just multiply by the denominator to move it over to the left side. I'm going to divide by 360. 1 plus 17/3 e to the negative 3b equals 1400 over 360. I'm going to reduce that. It's going to go down to 35/9. Again, I'm trying to avoid decimals which are rounded because that's going to influence my answer. I'm going to get rounding error if I'm not careful. Okay, I need to try to isolate this exponential right there. So first I need to subtract 1. 17/3 e to the negative 3b equals 35/9 minus 1, which is 9/9. 35/9 minus 9/9 is 26/9. I'm going to get rid of that 17/3 by multiplying by the reciprocal. E to the negative 3b will equal 26/9 times 17/3. Whoops, 3/17. The reciprocal, 3/17. Well, that reduces a little. 3 goes into 9 3 times. And I'm going to stick with my fraction. E to the negative 3b equals, well, that would be 26 over 51. 3 times 17 is 51. I've isolated my e, my exponential. So I'm going to change it to a logarithm in order to get up to that b in the exponent that I'm trying to solve for. So base e, so natural log of 26 over 51 must equal my exponent, negative 3b. So now I just need to divide that by negative 3, and I will have found my b value, my constant. So let's try that. Log 26 over 51 is all divided by a negative 3. And we want to list that b value out a long ways. 0.2245764. Now that I have my b value, I can answer their question A, which is determine the logistics model. So let me write the answer for A right over here. We know the population at time t is going to equal 1400 divided by 1 plus our 17/3 e raised to the negative b value, negative 0.2245764 times t. So there is my model, logistics model, for the population growth of these lovely coyotes. So they say, now, part B, use the model to predict to the nearest 10, or round to the nearest 10, the coyote population in the year 2014. Okay, well, if it's the year 2014, I need to know what t is going to equal. Now remember, our time 0 was 2001. So 2014 is 13 years later. T equals 13. So all we're doing is putting a 13 right there. So our population 13 years later should equal 1,400, 1 plus 17 thirds, e to the negative point. Try your calculator. Make sure you can enter that correctly. You would probably need a nice set of parentheses around that denominator. You may need a set of parentheses around this exponent here, depending on what your calculator operating system is like. So rounded, you should get 1,070. Now let's go back to this. It said population satisfies this model. Okay, yeah, that's it. 1,070 coyotes. All right, if you look on the syllabus in Google Classroom for the other review problem numbers, those are ones that you can use to study, so you are fully prepared for the test on next class period. The test will not include software where you have to fit equations to data. It will be things that you can do all by hand and with your calculator.